So atomic theory is the idea that matter is composed of atoms, and it grew out of some observations and laws, and those include the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. And we'll talk about each of these. We've already talked about the law of conservation of mass. In a chemical reaction, mass is neither created nor destroyed. And this was something that Antoine Lavoisier came up with back in the 1700s. So when a chemical reaction occurs, the total mass of substances doesn't change. So Lavoisier was burning things in closed containers. You weigh the closed container before the combustion, you weigh it after, it weighs the same amount because matter is conserved. So atomic theory explains this law by saying that the particles are just rearranging during a chemical reaction. None of the particles are created or destroyed. They're just being combined together in different ways, so of course the mass is going to stay the same. It's like building with Lego blocks. So here we have an illustration of a chemical reaction. Here's sodium. It's a solid, soft metal. You can cut it with a table knife. Here's chlorine gas. Chlorine gas exists as these diatomic molecules. And when we react these two together, they react somewhat violently to form sodium chloride. In sodium chloride now, we still have the sodium and the chlorine atoms, but they are arranged differently now. They're arranged in an alternating pattern. And so this is sodium chloride, which is table salt. You can't eat sodium. You can't breathe chlorine without having some serious health effects, and yet we do eat salt. Too much, of course, isn't good for you, but too little isn't good for you either. The mass of the products is equal to the mass of the reactant. So if you take 7.7 grams of sodium, that will react with 11.9 grams of chlorine, a total of 19.6 grams. You weigh the salt that gets produced, it weighs the same as the mass of the reactants. Another French chemist, Joseph Proust, made an observation about the composition of compounds, and this is summarized in the law of definite proportions. So all samples of a given compound, regardless of where they came from, how they were made, have the same proportion of their constituent elements. So we can use water as an example. If you take 18 grams of water and decompose it, it will decompose into 16 grams of oxygen and 2 grams of hydrogen. We see that mass is conserved because you started with 18 grams. At the end, you still have 18 grams. It's just different stuff. So we can look at the mass ratio, the ratio of oxygen to hydrogen. 16 grams of one to 2 grams of the other, that's an 8-to-1 ratio. Just to make the numbers nicer, always put the large number on top so that you don't have little tiny numbers. Doesn't matter how large the sample of water is, where it came from, you'll always get an 8-to-1 ratio by mass of oxygen to hydrogen from water. So this question is about the law of definite proportions. 2 samples of carbon monoxide are decomposed into their constituent elements. One sample produces 17.2 grams of oxygen and 12.9 grams of carbon. The other produces 10.5 grams of oxygen and 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. So the law says that the ratio of oxygen to carbon or carbon to oxygen should be the same for both samples. So the mass of oxygen is greater, so I'm going to put the oxygen on top, so 17.2 grams of oxygen divided by 12.9 grams of carbon. That's for sample 1. So 17.2 divided by 12.9, 1.3333, it's just repeating. We should always think about significant figures. Each of these numbers has 3 sig figs, and so that would be rounded to the 3rd significant digit. So the ratio is 1.33. And then we look at the other sample, and again, we want to do the same order. We want oxygen to carbon, just because that's what we did the first time. 10.5 grams of oxygen divided by 7.88 grams of carbon. And this time it tells me 1.33248, and it just keeps going. Here again, though, we have 3 significant figures. The ratios of oxygen to carbon are the same for both of these because they are the same compound. Compounds always have the same ratio of their constituent elements. Any questions? Then we have the law of multiple proportions, which, if you don't know what they are, it kind of seems to contradict. John Dalton again. The law of multiple proportions. This is one that's especially confusing when you just write it out, so it's going to take some explaining. When 2 elements, we'll just call them A and B, form 2 different compounds, the masses of element A that combine with 1 gram of the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. The reason this is because if you have 1 atom of A, it could combine with 1 atom of B. It might combine with 2 atoms of B or 3 atoms of B, but they have to be whole numbers because the atoms are the smallest particles. You can't have 1 atom of A and 1.5 atoms of B. You could have 2 atoms of A and 3 atoms of B, but they have to be small whole numbers. So the masses of B that react with A are related to each other as small whole number ratios. So basically, how we demonstrate this, in the previous problem we looked at the ratio of the masses and we found that they were the same. Here we're going to look at the ratio of masses, but it's 2 different compounds, and so now the ratios are different. But if we take the ratio of the ratios, right, that's not confusing at all. The ratio of the ratios gives us a small whole number. Might be 2, might be 3, could be 5, something like that. And that's because the individual atoms combine with each other in small whole number ratios. So example, carbon monoxide and carbon dioxide. 2 different compounds just containing carbon and oxygen. The mass ratio of oxygen to carbon in carbon dioxide is 2.67 to 1. So we could say that 2.67 grams of oxygen would react with 1 gram of carbon. In carbon monoxide, that's the one we looked at in the previous problem, the ratio was 1.33 to 1. 1.33 grams of oxygen for every 1 gram of carbon. So if we take the ratio of 2.67 to 1.33, we get a small whole number, 2. So the ratio of those ratios is itself a small whole number. Any questions? Yeah.
I don't know if we have time, but can we do an example?
That's an excellent question. Can we do an example? How about this one? Hydrogen and oxygen form both water and hydrogen peroxide. So if we decompose a sample of water, it's going to form 0.125 grams of hydrogen to every 1 gram of oxygen. The decomposition of hydrogen peroxide forms 0.250 grams of hydrogen to every 1 gram of oxygen. Show that these results are consistent with the law of multiple proportions. So for the water, the ratio is 0.125 grams of hydrogen to 1 gram of oxygen. And here they put oxygen on the bottom, and so we're getting less ratios that are less than 1. And for the hydrogen peroxide, the ratio is different. So this is 0.25 grams of hydrogen for every 1 gram of 1 gram of oxygen. So if the law of multiple proportions is true, then the ratio of 0.125 and 0.25 should be a whole number. Well, we need to put the bigger number on top, because otherwise we're going to get a number that's less than 1. So put the big number on top, 0.250, and divide by the smaller number, 0.125, and that gives us 2. What this is saying is that for hydrogen peroxide, I'm just going to leave it at that. Any questions? So we mentioned John Dalton's atomic theory in chapter 1, but we're going to talk about it a little more in depth. So his atomic theory explained those laws: conservation of mass, law of definite proportions, and law of multiple proportions. So each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that make them different from atoms of other elements. Atoms combine in simple whole number ratios to make compounds. And atoms of one element cannot change into atoms of another element. In a chemical reaction, we just rearrange the atoms. We change how they're stuck together. We do not change the individual atoms themselves. Now, there are 2 of these statements that had to be modified later based on new information. And this is an example of where you can take a theory or a law and you've got some evidence, some experiments that contradict it. You don't necessarily throw out the whole thing. Sometimes you just need to modify it. Anybody know which ones those are? Number 2. Yeah. All atoms of a given element have the same mass. Okay, that's not quite true. We're going to learn about isotopes. Same element, but they're a smidge different than each other, and their masses are not exactly the same. And then what's the other one? Number 4. Atoms of one element cannot change into atoms of another element. Well, it's true that that cannot happen in a chemical change, but in a nuclear reaction, elements can change into other elements. So Dalton's atomic theory, though, is still very useful because it describes stuff that happens outside of nuclear reactions. And nuclear reactions are uncommon. They are not the normal sort of chemical changes that occur.